Okay, so here in this particular kinematics problem, we have an object that is dropped from rest in the vertical motion. It says as shown in the diagram, and then it says neglecting air friction, aka in a vacuum, calculate the following. So we have A, B, C, D, E, and F. F is just a true or false statement. All right, so here we have a schematic at the bottom here. We have a hand that's dropping a ball or an object, whatever, from rest. And as you can see, as it falls, it picks up speed. The distance during each of these 1 second interval suggests that the gap is getting bigger and bigger, which implies that it's traveling more distance per second. All right, and then here in the top right, we have a little animation here of an object being dropped. As you can see, as it falls, an object picks up speed, which is, common sense. All right, let's do part A and B here. Part A asks you to find the displacement during the first second. To find the displacement during the first second, you have to start from 0 second to 1 second. So here in my work, I have my delta y is equal to VIT plus 1 half GT squared. I'm going to cross VI out because I'm going from time equal to 0 to just 1 second. If I start time equal to 0, it suggests that VI is 0 here in the chart, and then also my initial position is 0 as given. Okay. Therefore, pretty straightforward. All you have to do is plug in the g value for acceleration due to gravity at the surface of the Earth, which is accepted as negative 9.8 meters per second squared. And here, the time is 1 second, because from 0 to 1 second is just 1 second, and we want to square that. So really 1 half times negative 9.8 times 1, which would just give us a value of negative 4.9 meters. Here I highlight the direction there for you. The negative sign implies that the object is falling down. So our displacement is negative 4.9. So it's 4.9 below its starting point, aka y is equal to 0. Okay, so that's our answer for part A. Part B asks you to find the instantaneous velocity at 1 second. Well, to find the instantaneous velocity at 1 second, all we have to do is set up our VF function. VF is equal to AT plus VI. Here, our VI is 0, so really all we have to do is plug in A, which is G in this case, and G, again, is negative 9.8 meters per second squared. Our time here is 1 second because part B asks us for the instantaneous velocity at 1 second. All right, so that's pretty much it. So therefore, our velocity at 1 second is negative 9.8 meters per second. Okay, so that's our answer for part B. And then I want to go ahead and put that in the chart there. So just from part A, we know that it fell a distance of 4.9 downward. And then for part B, we know that the velocity at 1 second is negative 9.8 meters per second, which makes sense because acceleration is negative 9.8 meters per second square, which suggests that the velocity changes by negative 9.8 every second. All right, let's do part C. Here, part C is to find the average velocity during the interval of 1 to 3 seconds. The interval from 1 to 3 seconds is the difference of 2 seconds. Here, our starting point is 1 second, our ending point is 3 seconds. Keep that in mind. Therefore, to find average velocity, I need the vertical displacement divided by the change in time. My vertical displacement is given as VIT plus 1 half GT squared. Here I highlighted VI because VI is not 0 for this particular time interval. The problem starts at 1 second, which suggests that the object is already moving. Because it's already moving, its initial velocity cannot be 0. So here, VI is negative 9.8 from my part B. It just happens to be the same time here. Part B suggests that the velocity is negative 9.8 meters per second at 1 second. So since part C starts at 1 second, I would use the same velocity. So my initial velocity here is negative 9.8 meters per second. My time is 2 seconds because the difference from 1 to 3 seconds is 2 seconds. And then everything to the right is just plug and chug. G is negative 9.8 and then 2 for time, square that. So really here we have negative 19.6 meters plus another negative 19.6 if you punch your calculator working correctly. So negative 19.6 plus another negative 19.6 give us negative 39.2 meters. So now that we found our displacement, we're pretty much done with part C. We know our displacement now is negative 39.2 meters, and we know our change in time is 2 seconds because from 1 to 3 seconds is 2 seconds. So we just plug and chug. The numerator is negative 39.2 meters. The denominator is 2 seconds. So if we simplify that, we should get an average velocity of negative 19.6 meters per second. The answer is highlighted with the direction there because it asks for average velocity, which is a vector quantity. Okay, so you do need the sign here, or you can say 19.6 meters per second downward. Okay. All right, let's do part D. Okay. Actually, before we do part D, I forget. For part C, you can actually also use this kinematics equation, which is Vf plus Vi divided by 2 under constant acceleration. And our acceleration during free fall for this in a vacuum is constant. So we can do Vf plus Vi divided by 2. I like this function. I almost forgot about it. I like this function because it's super quick to do as long as you can find your V's super fast. Well, here our time interval is from 1 to 3 seconds. So hopefully by now, since we're doing vertical motion, that your horizontal kinematics is solid. We can find the velocity at 2 seconds. So if I can redirect your attention to the little chart down here. Well, the initial velocity is 0, and it picks up speed 9.8 every second. So it's going to go from 0 to negative 9.8, and then it's going to pick up another 9.8 in the next second. So the next velocity is going to be negative 19.6, and so on and so on. So each second that goes by, your velocity increases by a magnitude of 9.8. So here we have 0 plus 9.8 is 9.8, and then 9.8 plus another 9.8 is 19.6. 19.6 plus another 9.8 is 29.4, and then 29.4 plus another 9.8 is negative 32. You know, so the negative sign just implies that it's falling down. So if you know how to do this quickly in your head, I like this strategy because I can just go ahead and use the 2 velocity at the time given. Here I highlighted 1 second, and I'm also going to highlight 3 seconds because the time interval here is from 1 to 3. So I know my 2 velocities at these 2 point in times, so which is super fast to get. Okay, so I'm just going to replace Vf with negative 29.4, and then Vi with negative 9.8, and then want to sum those up and then divide it by 2. So if you sum up the numerator, you get a negative 39.2. Negative 39.2 divided by 2 will give us negative 19.6 meters per second, which is the same answer as the previous strategy using average velocity is equal to displacement over time. So which strategy you use, doesn't matter. Just pick one. All right, let's do part D now. The average speed during the first 5 seconds. The language here suggests that the initial time is equal to 0 second because it says the first 5 seconds, and our final time is going to be 5 seconds on the chart here. All right, so to find average speed, all we have to do is do distance over time. Well, we don't know what the distance is, but we can use our displacement function to find the distance because it's just falling downward. So the magnitude of our delta y here is the distance. Again, the only difference between distance and displacement is one has a direction, one doesn't. If an object moves one way, which it is in this case. Vi here is going to be 0 because it says the first 5 seconds suggests that we got to start at times equal to 0. At times equal to 0, Vi is 0 based on the chart and based on the wording. It says drop, so from rest, okay? Therefore, it just becomes a plug and chug here. G is negative 9.8. Time here is 5 seconds. First 5 seconds, again, imply a time interval of 5 seconds. If we square the 5, which is 25, we times that by negative 9.8, times that by a half, we should get a displacement of negative 122.5 meters. But we just need distance, so really just do absolute value. So here, average speed is simply distance over time. So instead of plugging in a negative 122.5, I'm just going to use 122.5 and then divided by 5 seconds, which is a value of 24.5 meters per second. You don't need any directions because average speed is a scalar. Okay, or you can use the average velocity function again that I exercised in part C. Again, I can just use this function here because I can find the average, and the only difference between average velocity and average speed when an object goes in one direction is that the answer has the answer has a direction for velocity, but if it's speed, then you can just leave the direction out. Here, all we have to know is know where Vf is, know where Vi is. Well, for this particular part, it's just the first 5 seconds implies that our final time is at 5 seconds, and then our initial is at 0 second. So I'm just going to highlight the 2 velocities that I'm interested in. Okay, Vi is 0, so I'm going to cross that out, and then Vf in the box here on the left side. Okay, so here I highlighted at times equal to 0, V is equal to 0, and I'm going to highlight 5 seconds. At 5 seconds, the velocity is negative 49 meters per second. It's falling down. So I'm just going to plug in Vf as negative 4.49. Excuse me, Vf is negative 49, and then divided by 2. Therefore, negative 49 divided by 2 is negative 24.5. But Again, part D asks for average speed, so I'm just going to do the absolute value of my answer. So really just leave out the negative sign in front. So our answer here is just 24.5 meters per second. All right, let's do part E. Part E asks us to find the distance traveled during the third second. So I'll do this properly, and then I'll hopefully encourage you to use ratio if you are good at functions. Here, to find the distance traveled during the third second, it would imply that the object starts at 2 and ends at 3 seconds. So if you can watch my cursor, from 0 to 1 second, it is known as the first second. From 1 to 2 second, it is known as the second second. And then from 2 to 3 second, it is known as the third second. So the third second suggests that you start at 2 seconds and you end at 3, which is 1 second interval. All right, because we start at 2 seconds, my VI is not 0. Okay, so pay attention again to starting time. My VI here is actually negative 19.6 because at 2 seconds, according to this chart, again, if you can add up all the velocities quickly based on your acceleration value, you can do these problems with minimal pain. VI here is negative 19.6 because my initial starting time is at 2 seconds based on the wording. My change in time here is only 1 second though, okay? Even though it says the third second is from 2 to 3 seconds, which is a 1 second difference. So we just use 1 second. All right, everything else is plug and chug. If we simplify this, we get negative 19.6, and then 1/2 times negative 9.8 times 1 square is negative 4.9. Here we have a negative plus a negative, so it gives us even a bigger negative value, so negative 24.5 meters. And then, but it asks for distance though, so to find distance, again, we just got to recognize that distance is a scalar. So really, it fell down 24.5, but we don't really care for the direction, so we can just say that it fell a distance of 24.5 meters, and that's our answer for part E without the direction. Okay, so again, distance is a scalar. You don't need to include any sort of direction in your final statement. All right, here I would encourage you, if you know how to do ratio, this is super quick. Watch the numbers come on the screen. From 0 to 1 second, I know the object has fallen a distance of 4.9. But what I can do is I can go from 0 to 2. Well, from 0 to 2 is twice the amount of time as it is from 0 to 1. Well, according to this particular displacement function, your t is square. So anytime you go from 0 to 1 and it has fallen 4.9 meters, well, going from 0 to 2 doubles the time, but doubling the time quadruples your distance in this scenario because VI is 0. Okay, so this is an important condition. Since it's being dropped, I know this ratio is true. So the first second, it has fallen 4.9. So therefore, after 2 seconds, it would fall 4 times as much because t is square. So 2 squared would be a 4. So if you take 4.9 times 4, it will get you 19.6. But then I can use that same strategy again and go from 0 to 3 seconds. Well, from 0 to 3 is tripling the time from 0 to 1. So if I know that during the first second it has fallen just 4.9 meters, from 0 to 3 it would actually fall 9 times the distance because the t in this particular kinematic equation is a quadratic term. All right, so if you know how to do that, it'd be 4.9 times 9. That would tell us that it has fallen 9 times as much during the first 3 seconds. So therefore the distance fallen is 44.1. But once we know these values, we can just take the difference. Well, here the position is negative 19.6, and then it's going to go down to negative 44.1. So really, during 2 to 3 seconds, it has fallen a distance of when I said distance, it has fallen a distance of 24.5. Here in my work, I have it as negative because it's technically, traveling downward. But since we're talking about distance, we can just do the absolute value of that. But this is a quick strategy if you know how to do ratio without doing a lot of math and tedious busy work. Okay, so listen to it if you need to. All right, but the other way to do it, if you like using these kinematics equations, just to make sure that your answer is right, we can use the two average velocity functions, set them equal to each other. Here I have delta x over delta t is equal to vf plus vi divided by 2. But you can replace delta x with delta y if you like. It doesn't really matter. Just know that the object's falling vertically. So delta x, delta y, whatever makes you comfortable. If you're paranoid, I would say change delta x to change delta x to delta y, so that you're not tripping. All right, but to solve for delta x, all we have to do is, multiply both sides by t, and then we just have to recognize our VF and VI. The stuff that came on the screen just now, I know here it's just the third second, so I'm going to start at 2 seconds, I'm going to end at 3 seconds, and then the time interval is just 1, okay? So I'm doing the algebra step here just so that I can see, but really the third second would imply that delta t is just 1 second. So anytime you multiply or divide by 1, it's kind of redundant. But I'll do it just in case you need to do algebra if delta t is not 1. To get delta x by itself, just multiply both sides by delta t. And that'll get rid of the denominator delta t on the left hand side, but then multiplying the right side by delta t would give us a function that looks like this right here where I'm tracing back and forth. So really it's just VF plus VI divided by 2, and then we're going to multiply that whole quantity by delta t. So make sure you do your algebra correctly. Here, VF is negative 29.4 meters per second because at 3 seconds, that's how fast it's moving in the downward direction. And then at 2 seconds, it is moving at a rate of negative 19.6, which is what I've boxed in blue here to the left. So you notice here my starting time at 2 seconds, my ending time is at 3 seconds, and I know these two velocities already, if you can just add 9.8 every time quickly in your head or calculator. All right, so if we simplify all this work, we get the numerator is negative 49, and then divided by 2 times 1 second on the outside. And then if you do that, your answer is negative 24.5. But here, that is your displacement in the downward direction. But to find distance, you would just do the absolute value. So our answer would simply just be a distance of 24.5 meters, okay? And then part E is true because it says here the average speed increases during each second interval. It's true because as an object falls, it picks up speed. As it picks up speed, it covers more distance each second. So average speed is distance over time. Well, it says during each second, so t would just be 1 second, but the numerator would be bigger, okay? So once again, slower. Speed equals distance over time. The time during each second is just 1 second, so it stays a constant. But the d in the numerator is what you're assessing. Well, as it falls, it picks up speed, and during each second, it picks up speed, therefore it covers more distance. So therefore, increasing d in the numerator would cause your value to increase as well. So this statement is true for that reason. The average speed increases during each second because the distance covered each second increases. All right, I hope that helps. Good luck, stay nerdy, don't be whack.